Today, we're going to break down something that's been called the operating system for AI. It's a framework called RHOAI, and it was built to power the next huge wave of intelligent applications. So let's dive right in and figure out what that really means. First, let me ask you a question. How do we get from an AI that just recognizes stuff to an AI that actually learns by doing? Trial and error. Think about a robot learning to walk for the first time, or a system mastering a super complex game. It's not about having all the answers right at the start. It's about learning by constantly interacting with the world around it. And here's the catch. The tools and frameworks that got us through the first big AI boom, well, they just aren't built for this new, dynamic world. They were designed to solve a completely different kind of problem. And that brings us right to the heart of the new AI challenge. We're moving beyond what's called supervised learning and into a world that's way more complex and honestly, way more powerful. That new world is called reinforcement learning, or just RL for short. At its core, it's pretty simple to grasp. You've got an AI agent, think of it like a player in a video game, and it's learning how to make the best decisions by just playing the game. It tries stuff, sees what happens, gets points or loses points, and over again, it tweaks its strategy to get the highest score possible. So let's put these two worlds side by side. On the left, you've got the past, supervised learning. This is where you train an AI offline with a massive fixed data set, like millions of labeled pictures, so it can learn to do one thing really well, like spot cats in photos. But on the right, you've got the future, reinforcement learning. It learns by doing, by constantly interacting with a live, ever-changing environment. This is exactly how AlphaGo didn't just learn the rules of Go. It learned strategies that allowed it to beat the best human player on the planet. And this right here is where our old tools start to break down. The systems that were built for that static, predictable world of supervised learning, well, they just can't keep up with the insane demands of this new interactive reinforcement learning world. I mean, just look at what this new AI demands. It has to make decisions in the blink of an eye. We're talking low latency. It's got to juggle millions of tiny simulations all at once. That's high throughput. And the AI's entire game plan can change with every single move, so the system has to be incredibly flexible, not rigid. That's what we mean by dynamic graphs. On top of all that, it's juggling all kinds of different jobs, from tiny little calculations to massive heavy-duty training runs. It is a chaotic, super demanding environment that older systems were just never designed to handle. So here's the bottom line. Popular frameworks you might know, like Spark or TensorFlow, are incredibly powerful, but they were designed with a key assumption that the world is static and predictable. They just don't have the fundamental architecture needed for the kind of speed, scale, and chaotic flexibility that modern AI demands. And this is exactly where RHOAI enters the picture. It was built from the ground up to solve these very problems, giving us a single, unified framework for this completely new era of AI. The creators of RHOAI put it perfectly in their paper. RHOAI's real genius is this unified interface. It's able to handle two very, very different kinds of work, what they call task parallel and actor-based computations, all using one incredibly powerful dynamic engine. Okay, so what are these two models? On the left, you have stateless tasks. The best analogy is a freelance calculator. You call it up, give it a quick one-off job, it gives you an answer, and you're done. No memory, no history. These are perfect for running millions of tiny independent simulations. Then on the right, you have stateful actors. This is totally different. This is like your company's full-time accountant who knows your entire financial history. Actors have memory, they maintain state, they're perfect for the heavy lifting, like training a model over time or managing a complex simulation. And RHOAI's magic is that it unifies both of these seamlessly. All right, so that's the what. Now for the how. Let's take a quick peek under the hood to see how RHOAI actually pulls all this off. RHOAI's architecture really comes down to three core superpowers. You've got a brain, called the global control store, you've got a super efficient nervous system, the bottom-up scheduler, and you've got a high-speed short-term memory, the in-memory object store. These three things working together are what give it its incredible performance. So first up, the brain. The global control store, or GCS, is the single source of truth for the entire system. It tracks absolutely everything. And by putting all the big picture state here, it allows every other part of RHOAI to be stateless, meaning they don't have to remember anything. This is such a brilliant design choice. If a worker machine fails, you just restart it. No complicated state to recover. It's what makes the whole system so resilient and so easy to scale up. Next up is RHOAI's nervous system, this bottom-up scheduler. This is the secret to its insane speed. So check it out. When a new task comes in, it doesn't go wait in some long central line. Nope. Step 1, it goes straight to the local scheduler on its own machine. That scheduler tries to run the task right there, right then, for maximum speed. It's only if that local machine is totally swamped that the task gets passed up to the global scheduler, which then finds the perfect home for it somewhere else in the cluster. This local-first approach is what allows RHOAI to make decisions in milliseconds.
So the architecture sounds amazing in theory, right? But does it actually work in practice? Well, let's look at the numbers from the original research paper. And here is the headline number, 1.8 million. That's how many tasks per second RHOAI was able to process on a cluster. But what's even more impressive is that its performance scaled almost perfectly as they added more machines. That proves the architecture doesn't have bottlenecks holding it back.
And this chart shows what that speed really means. You can see RHOAI achieving almost double the simulation throughput of a more traditional system. And the reason is that RHOAI works asynchronously. It doesn't wait for every single task in a big batch to finish before moving on. It keeps the entire system firing on all cylinders, all the time, which just means you get your results way faster.
Okay, so what does all of this actually mean? All this performance, all this flexibility, why does a system like RHOAI really matter for the future of AI? Well, it matters because it unlocks the kind of applications that, honestly, we've all been dreaming about. We're talking about robots that can learn to pick up and use objects they've never seen before, self-driving cars that can truly adapt to chaotic city streets, and chatbots that feel genuinely conversational and adaptive. RHOAI provides the fundamental computational backbone that makes these incredibly complex, dynamic AI systems actually possible to build.
So in the end, RHOAI is so much more than just a framework. It really is an engine. It's the engine for a new generation of AI that learns, adapts, and interacts with our world. And that leaves us with one final big question. Now that we have this kind of new power, what are we going to build with it?